Welcome back to Fundamental Computer Organization and Architecture. Now let's concentrate on the memory hierarchy. We'll first talk about cache memories, and then we will deal with virtual memory in another video. Ideally, as a programmer, we'd like to have a memory abstraction which lets us view the memory as one large continuous array of memory cells, and that we can access any location anytime, a true random access memory, or RAM. Reality is different. First of all, with 64-bit addresses, as 64-bit processors have, we can address a whopping 16 exabytes of memory. That's roughly a billion times a billion. There is no way we can even build a machine with that amount of physical memory. Secondly, it's also a fact that large memories are slow and small memories are fast. Therefore, in high-performance computer systems, we always organize the memory in a memory hierarchy. The concept of a memory hierarchy means that you organize the memory in a computer in a hierarchy such that closer to the CPU you have small and fast memory to hold frequently used data, and only when you cannot find what you want in the fast memory you look in the larger slow memory. The register file, RF, can be seen as being part of the memory hierarchy and is the fastest storage option of them all. It is, however, managed from program, and you have to explicitly move data to the register file. Register files, as well as other fast memories that you find in the same chip as the CPU, are built with a technology called SRAM, Static Random Access Memory. In contrast, larger memories are outside the CPU chip and built from a technology called DRAM, Dynamic Random Access Memory. DRAMs can be packed much more compactly, and they are therefore both larger in capacity and cheaper. They are, however, also considerably slower, both because of the inherent way DRAM memory cells are built, but also because they have to be off-chip because of the way they are manufactured. DRAM memory cells are built from a single transistor, and the memory contents is represented by a charge in a storage capacitor. The transistor works like a switch, and with the 1 on the gate, the line at the top here, a current can flow between the capacitor and the bit line. Assume we have a charge in the capacitor. That represents the value 1. We have also pre-charged the bit line to a voltage between 0 and 1. To read the value of the cell, we set the bit line to 1. This will open the transistor and let the capacitor discharge to the bit line, which is at a lower voltage. Sense amplifiers at the bit line will sense this small current and detect that we just read the value 1. If there was no charge, the current would be in the opposite direction, charging the capacitor from the bit line when the transistor opens, and we would detect the value 0. Note that by reading the value of a cell, you also destroy its value, so it has to be written back, which takes time. Over time, the charge in the cell will also discharge because of leakage currents in the transistor. Therefore, even if you're not reading or writing the memory cells, needs to be refreshing. Read and written back every 64 milliseconds with the current DRAM techniques. DRAM cells are organized in two-dimensional arrays on chip, as square as possible. The array is addressed with half of the address first selecting a word line through the row address decoder. The whole row is read and stored in a row buffer. The second half of the address is used to select the number of bits from the row buffer. If the next address access is from the same row buffer, then faster access can be done. The performance of high-performance computers is typically limited by memory bandwidth and latency. The latency is the time it takes to make a single memory access, which is generally a lot larger than the clock cycle time of the processor itself. The bandwidth is measured in bytes per second, and the request for bandwidth depends on how many instructions per second you execute and how many memory references each instruction needs to do on average. There is in fact a growing gap between CPU speed and DRAM memory speed. Why doesn't DRAM get faster? One simple reason is that growing demand of large memories also lead to physically larger structures. The signals will have to travel longer distances, which takes significant time in comparison with the speed we clock processors. So, how is the memory hierarchy managed? Register files are managed entirely in software. The addresses to registers are integrated in the instruction code itself because you only have a handful of them. There might be hardware that do things like register renaming with the software unknowing, but we will talk more about that when we discuss superscalar processors. The main memory, however, is augmented by a cache hierarchy which will provide the illusion of a faster memory with the large memory's capacity. The reason for why you can build an illusion of a fast and large memory is because software programs exhibit certain memory reference patterns. The image here comes from an old measurement showcasing how memory references are distributed over time. Here are some typical memory reference patterns you might see. Instruction fetches may look like this. You typically see sequential access of addresses which may be repeated sometimes when you have loops. Stack accesses also have a distinct access pattern. As you make subroutine calls, data is pushed on the stack, return address and other callers save their registers, and during the execution of a subroutine, you might access an argument that has been stored on the stack, and then the subroutine returns. Accesses to global data or data on the heap can have yet another pattern. In scientific code, you might observe sequential access through a vector, or repeated access to the same memory address if it's a scalar access. In general, we can observe two kinds of predictable properties for memory references. Temporal locality. If a location is referenced, it's likely to be referenced again in the near future. Spatial locality. If a location is referenced, it's likely that location near it will be referenced in the near future. Here we go back to the data from IBM showing examples of two kinds of locality: temporal locality and spatial locality. Cache memories is a way to build a cache hierarchy that exploits both kinds of locality. We exploit temporal locality by remembering the contents of recently accessed locations, and we exploit spatial locality by fetching blocks of data around recently accessed locations. The word cache comes from the French word cacher, which means hide away. So the cache is essentially a hardware-managed memory structure between the processor and the main memory. The idea is that we address the cache using a physical address. We search in the cache if the value is in the cache. If it's not, we fetch it from the main memory and places it in the cache. In order to exploit spatial locality, we fetch not only exactly what is requested, but also some amount of data around the requested datum. The amount of data fetched from memory to the cache is called a block. The cache is organized as a memory structure with a number of lines. Each line can hold a block. A cache line can hold any data block from memory. In order to distinguish different data blocks from each other in a line, a portion of the address to the block is stored together with the block as part of the line. This field is called an address tag. It's not the entire address that is stored in the tag, but only enough bits to uniquely identify the block. Important terminology here are data block, which is the amount of data fetched from memory to be stored in the cache; cache line, a storage space in the cache with the same size of a block; address tag, a field associated with the cache line uniquely identifying the block. This is what happens in the cache when you have a read access. If the data is found in the cache, we say that we have a cache hit and simply return the data from the cache. If it is not found, we say that we have a cache miss and we need to read a block of data from the memory and wait for it to come back. When it eventually comes from memory, we update the cache and returns the value requested to the processor. The processor needs to be able to cope with variable access times, just like a stall. A number of questions arise. For instance, how do we search for a block in the first place? And where do we put a block when there is a miss? Before talking about how to find a block in the cache, it's useful to talk about memory addresses and how we can divide an address in different parts. As mentioned, we divide the address space into blocks of equal size. The size of a block can be calculated as a power of 2, where the size is 2 to the power of b. So for instance, if we set b to 6, then the size of a block is 2 to the power of 6, which is 64 bytes. We can then divide the memory address into one part called the block offset, which represents which byte in the block we want to access, and the other part called block number, which identifies the block uniquely. We are now ready to discuss how to place a block in the cache. We need a way to figure out in which cache line we can place a block, and this will also be useful when we look forward. The figure here shows a small memory consisting of 32 blocks numbered from 0 to 31. We also have a small cache with space for 8 cache lines numbered 0 to 7. The simplest scheme to figure out in which cache line to place a block is to select a number of bits in the block number, which will uniquely select a cache line where to place the block. The number of bits should be chosen to fully address the number of lines. In the example here at the bottom right, you have 8 lines, so you would need 3 bits to select one line out of 8. So assume you want to place block 12, which is 01100 binary. You take the 3 least significant bits 100, and therefore the block can be placed in cache line number 4. The mathematical calculation done here is 12 modulus 8, which is equal to taking the 3 least significant bits, as the cache size is a power of 2. This method is called direct mapped. It's simple to implement, as we soon will see, but the drawback is that we might have multiple blocks that we want to use frequently, and then we will have conflicts and they will push each other out. Another option is that you have full choice of where to place a block. That is, you just pick a free cache line and use it. This is called a fully associative placement. This does not have the same drawback as direct mapped, but it's significantly more complicated to build in practice. In reality, many caches are implemented using a hybrid called set associative address mapping. The figure in the middle bottom shows a two-way set associative mapping. The cache lines are grouped in sets, and some bits from the block number are used to identify a set where the block can be placed. The number of sets must be a power of 2, just as the number of lines in a direct mapped cache must be a power of 2. In the example, we have 4 sets, which means that we use the 2 least significant bits in the block number 01100, which is 00. Thus, the block is placed in set number 0. Within the set, the block can be placed in either line. Let's now look at how you can implement these in practice. This image shows the design of a direct map cache. At the top you have the memory address issued by the processor. The cache contains 2 to the power of k lines, so k bits from the block number is used to select the cache line. This is the only line that could contain the block, but the contents of the line may be from a different block, so we compare the remainder of the block number, also called address tag, with the value that is stored in the cache line. If they are equal, we have a cache hit. If the cache line also is valid, which is denoted by the valid bit v. The valid bit is useful, for instance, when the processor is starting, when all valid bits are set to 0. When we know we have a hit, we can select the right word using the block offset and send it back to the processor. Now consider a two-way set associative cache. It's very similar to a direct mapped cache, but instead of selecting one single cache line with the block index, you select a set, which in this case consists of 2 lines. We need to compare the tags of both lines with the address in parallel, and if one of them matches, we have a hit. For the same size of cache, this mapping has half the number of sets compared to the number of lines in a direct map cache. The index field is therefore 1 bit smaller, and consequently the tag is 1 bit larger. In the fully associative cache, there is no index, and we need to compare the tag of all cache lines simultaneously. This is impracticable for all but very small caches, and is therefore used only for specialized purposes. In a set associative cache, which can often be 4-way to 12-way, you need to select one of the lines to evict when the selected set is full of valid blocks. How do you do that? There are a number of methods which have been proposed and investigated, and the most important ones are random and LRU. The random method simply selects a cache line randomly and replaces it with the block fetched from memory. It's simple to implement and will not affect the hit time. LRU means least recently used and was first developed to be used in virtual memory. The premise is that the line that was used longest time ago is probably not going to be used again, and we choose that to evict. A precise implementation can be quite complicated, so a pseudo LRU algorithm is often used. The reason for why random is not completely poor choice is that it's only a second order effect. Why? Because replacement only happens on misses, and hopefully this is a rare event. The cache, as we have talked about so far, is good for making use of temporal locality. What about spatial locality? This is why the block is larger than a word. Larger blocks exploit spatial locality and can also utilize the fast burst transfers from DRAMs and utilize wider buses. However, with larger blocks, there will be fewer blocks in the cache and therefore more conflicts in the cache. If the entire block is not used, we might waste memory bandwidth by fetching blocks not needed. The final thing we need to consider when it comes to cache memories is what happens at store instructions who write to memory. If there is a cache hit, we have two options. The write could be done in both the cache and in the memory, write through, or we could just perform the write in the cache, called write back. If we choose the write back option, we need to mark the line in the cache that have been modified so that they are written back to memory when they are replaced. This is called dirty bit, as we say that the line is dirty when modified. Furthermore, we need to decide what to do upon a cache miss. We can choose not to bring the block in memory and just perform the write in the memory. No write allocate. Alternatively, we can first bring in the block to the cache and then perform the write, called write allocate. As always, there are trade-offs for all choices, and the best is workload dependent. It's common to combine write through with no write allocate and write back with write allocate. We have now come to an end in our review of cache memories, and we look at virtual memory quickly in the next video.